A few years back, I was working in a class and we had a conversation that led me to focus on how I think that many of us, students and everyone else in the world, may be losing a sense of the larger context of our lives. And so I thought about how I could do something about that. What could I do to help us regain a sense of ourselves in the context of the larger reality of existence? And so I've started to put together a slideshow because that's what I do. And when you start to think about what the context of our lives is, or when I did anyway, it got bigger and bigger and bigger until finally it got as big as it's possible to get. And it extended to the depths of the cosmos. And so my presentation is called, What is Our Place in the Cosmos? When I think about my place in the cosmos, I start with my family on my front porch. My wife, Christy, my dog, Abby, and especially now my 4-year-old daughter, Maddie, who are my centering place in the cosmos. But once we have all attached to our family, if you pull back a little bit from that and take a little bit larger context, you might see me in a picture like this. You might find Christy and me if you were very careful. Actually, we're not in this picture, but if we were, you might be able to find us in this picture. But if we pull back a little bit further, you probably would have a hard time finding us in this picture. 2013 game, UT-OU, UT won, hook 'em horns, but it would be difficult to find us in the context of the Cotton Bowl. Pull back a little bit further and we've got all of the Dallas-Fort Worth area, definitely difficult to find us. Pull back a little bit further and here is most of Texas. And we go back even further from that and we have the United States and all of North America, in fact, showing where we are, where we live. If you look closely, you can find the bright dot in that screen that represents Dallas, the Dallas-Fort Worth area, which is where we are. That is the context of our lives. When I see this image, one of the things that strikes me is how anthropologists will tell us that one of the ways you can tell about the advancement of a culture is how well lit it is at night. That seems so superficial, and it's a little bit offensive, maybe. But when I then see a picture like this, I think maybe that's true. This is a picture of the Korean Peninsula. You can see South Korea and the big, huge spot of Seoul, South Korea, the capital of South Korea, and then North Korea. This is not a retouched image. This is not a Photoshop. That is really an image of the Korean Peninsula. You can see the one dot there, the bright dot in North Korea. That is Pyongyang, the capital of North Korea. And if you look closely, you might be able to see some lights right there along the coast, the ocean of North Korea, and those lights are at military bases. And so the only lights you see in North Korea are the capital city and some military bases. And so maybe there is something to the fact or the claim that the more advanced we are, the better lit we are at night. But be that as it may, if you pull back from there even, here is an image that is interesting to me. This shows the United States, the lower 48, overlaid on the moon, as if you had taken a knife and sliced off the surface of the 48 states. This is to correct scale. If we sliced off the surface of the United States, overlaid it on the moon, this is what it would look like. And so you can get a context of the United States and see sort of how we are, how we size up. Here's a similar image for all of North America, overlaid on Mars. Take a knife, slice off the surface of North America, overlay it on the planet Mars. This is how it would look. Now, Mars is a fascinating place. We've wondered about Mars for a long, long time. We've looked at Mars and you can see the red tinge of Mars, and people have studied Mars and looked at Mars for thousands of years, and we see the red tinge and we see the occasional retrograde motion of Mars, and people have studied it and wondered about it. When Percival Lowell did that back at the turn of the previous century, looked at Mars through his telescope, he thought he saw channels where a civilization, a dying civilization on Mars, was trying to move water from the polar regions to the parched remaining urban areas. And so he drew this map showing what he believed to be canals or channels on Mars. And so this is how he saw Mars. And so that image of Mars really took hold. And thousands of pages of science fiction have been written about that image of Mars, most of which I've read. And you can see here how artists pictured Mars with the canals and the dying civilization and the Martians looking to skies, wondering if there's going to be any redemption for their civilization. But this is not really how Mars looks. We know now this is how Mars looks. How do we know that? Because we have been able to study Mars, not with just our naked eyes, but with advanced scientific instruments, including numerous rovers that we have sent and others have sent to Mars. Actually, only one other has sent a rover to Mars. Currently, Curiosity and Perseverance are still operating on the surface of Mars. And if you can see the little white circle there, that's around the Ingenuity helicopter that was carried with Perseverance to the surface of Mars. Up there in the corner there is Zhurong. That is a Chinese rover that is the first non-American rover to land on the surface of Mars, first non-American rover. So that was great. Now these others have been there and have died. Actually, InSight is not a rover at all. It's just a lander, and it's still there working, but it's not a rover. It's a seismograph and a weather station. So we've still got a lot of science to do on Mars, looking forward perhaps to actually going there someday. But we know a lot about Mars because we've studied it. And one of the things we've learned about Mars is that there was a time in the long past when Mars was a watery planet, just as Earth is. In fact, for the first 1.5 billion years of Mars's existence, it was a largely watery planet with an ocean that covered at least 20% of the surface of Mars. And so for 1.5 billion years, Mars was a watery planet. And one of the things we know that on Earth at least, where there's water, there's life. And we also know that by the time Earth was 1.5 billion years old, life was well established here. Was life well established on Mars after 1.5 billion years of watery existence? Perhaps. We don't know. There are indications that are consistent with life on Mars, past life on Mars, perhaps even current life on Mars. But we certainly haven't proven that, and it's possible that there never was and certainly isn't life on Mars today. But we do know, once again, where there's water, there's life, and there was water on Mars. There was a lot of it. How do we know that? Well, we know it from a number of avenues of research. One is because we can essentially see it flowing on the surface of Mars. Here is a Newton crater where liquid, thought to be briny water, flows down the wall of this crater. We also have very graphic images of delta regions on Mars, which can only be explained by the flow of water or of a fluid like water that is what Perseverance is studying today. And so we know with a high degree of confidence that there was water on Mars. We also know that there's an excellent possibility that there is still liquid water subsurface on Mars. The Mars Express radar imager took these images of Mars using subsurface radar imaging, and these areas about 1.5 kilometers below the surface look like liquid water. We're not sure of that yet, but it's possible, but the most likely explanation for these radar images is liquid water under the surface of Mars. We'll see. Over time, as science advances and as we hopefully go there ourselves, we'll know for sure whether there really is existing liquid water on Mars, and subsequently whether there's life on Mars or whether there ever was life on Mars. Another way to think about the existence of life on Mars is methane. Methane is generally, not exclusively, but generally on Earth produced by life. We have a lot of methane on Earth, and most of it is produced by life. we have discovered methane in the atmosphere of Mars. And so once again, this is far from proof of life on Mars existing today, but it is consistent with life on Mars. There are other ways that methane could be produced, but life is one of them. And you can look at this, and this is a complicated scientific slide. I'm not going to try to explain it all. I'm not sure that I could explain it all. I can say that one of the ways that methane could be produced is a process known as perchlorate deliquescence, which I'll leave you to discuss with your chemistry professor. But we know that there's methane, and frequently methane is an indicator of life processes. One of the things we do know about Mars and potential for past life is that past life on Mars carved this face on Mars. Actually, that's not really true. That 1971 image from the Mars Viking orbiter looked like a face for a long time, but we now know that it wasn't. This is what was thought to be the face on Mars, and so there is no face on Mars. Sorry, folks. But there is a smiley face on Mars, and each Valentine's Day you can find plenty of hearts on Mars. And so we do have a lot of lifelike craters and experiences on Mars. So there we go. But life on Mars, what about life in the solar system? It's entirely possible that there is life elsewhere in the solar system. Once again, working on the assumption now, and it's only an assumption, that where there's water, there's life. We know that the moon of Saturn, Enceladus, has water geysers, and this image that you see on the slide is an image of water geysers showering up through the surface of Enceladus. And we are planning one of these days in the not too distant future to send an orbiter to Enceladus to fly through one of those geysers and bring back some water from Enceladus so we can test it to see if there perhaps could be life in a subsurface ocean on Enceladus. And we know with a high degree of confidence that there are subsurface oceans throughout our solar system. In fact, this image, which you can't see very well, it's a little bit small, but it will show you where there is thought to be water, liquid water, not frozen water, on the surface, or under the surface rather, of planets and moons throughout the solar system. We know that there is a lot of water on Earth, and we think of Earth having a lot of water. In fact, there is about 1.3 zetaliters of water on Earth. And 1 zetaliter is about 319 million cubic miles of water. So there's a lot of water on Earth. But actually, there are other places in the solar system that have a lot more liquid water, it is believed, than Earth does. In fact, Ganymede, the largest moon of Jupiter and the largest moon in the solar system, larger than our moon, larger than the planet Mercury, Ganymede has 35 zetaliters of water in a subsurface ocean that is kept liquid, kept from freezing, largely by the tidal effects from Jupiter, the pushing and pulling, the squeezing of Ganymede from the immense gravity of Jupiter keeps that water liquid. And so there's a lot of water in a lot of places in the solar system. And once again, going on the assumption that where there's water, there's life, it's entirely possible that there is life in these other places in the solar system. We'll see. One of these days, one of these years, one of these centuries, we will find out the answers to those questions. Going back to where I was headed before, this is an image that I love. This is Saturn, once again showing the scale of the Earth against other objects in the solar system. You can see here 6 Earths, the diameter of 6 Earths laid against the rings of Saturn. So Saturn is an enormous place by comparison with the Earth. But by comparison with Jupiter, Saturn is not so big. Here is, once again, it's a little hard to see because North America is so small, but here is North America overlaid to scale, to the appropriate scale, on the surface of Jupiter, right next to what we call the Great Red Spot. The Great Red Spot is that very famous, we all have heard of the Great Red Spot, first identified in the year 1608 by a Dutchman named Hans Lippershey. And so we know that the Great Red Spot has been a persistent storm in the atmosphere of Jupiter since at least the year 1608. We don't know how far before that, because that's the first time it was identified and described. But the Great Red Spot is much bigger than the Earth and is a huge storm on the surface. But you can see the context of Earth against Jupiter. But if you think Jupiter's large, how about this? Here is the sun, and there is Earth shown to scale next to the sun. Not to scale distance-wise. If we were that close to the sun, we would be vaporized. But there is an image that shows the size of the Earth next to the sun. So the Earth is a tiny place next to the enormous sun. Now the sun is about 99.2, I think, percent of the entire mass of the solar system. So if you add up all the planets, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, if you add up the minor planets, Ceres, Pluto, Haumea, Makemake, and Eris, if you line up all of the asteroids, all of the comets, all of the dust, all of the gas, the Oort cloud, all of it, it adds up to less than 1% of the mass of the galaxy, and mass of the solar system, excuse me. And the rest of the mass of the solar system is contained in the sun itself. And the sun has been burning 600,000 tons of hydrogen per second for 5 billion years now. And there's enough of it that it will continue to burn that hydrogen for another 5 billion years before the sun goes dark. And so there's an enormous mass associated with the sun. And it is hard for us to grasp the scale involved. But the scale of the sun, and I should say, if you ever have a chance to go see the sun, the surface of the sun, you can do that. I've seen the sun from the McDonald Observatory out in West Texas. They have these telescopes there, and you can look through the telescopes, properly filtered, obviously. You never want to look directly at the sun, as we all learn as children, and that is a good thing to learn. But if you look through a properly filtered telescope, you can actually see the surface of the sun boiling and roiling, and if you're fortunate, you can see a solar flare or a solar prominence. And so this is how the sun looks in real life. This is a photograph taken from the SOHO, the solar orbiter, and it is a fascinating thing to see the sun actually burning, boiling as it does. One of the interesting things that we think about the solar system is how, and about the Earth as related to the sun, is that we rotate around the sun, right? Everybody knows that. We rotate around the sun. Well, from one perspective, yes, that's true. But again, it all depends on your perspective, because from another perspective, that's really not true at all. What happens is that the Earth and the sun together rotate around a third point in space known as the barycenter of the Earth-Sun system. You can see that effect here in this image. Now, this is not the Earth and the Sun. This is Pluto, the minor planet Pluto, formerly full-blown planet, now minor planet. Sorry for all you Pluto fans, but this is Pluto and its largest moon, Charon. And you can see that the way Charon orbits Pluto, the gravity of Pluto pulls on Charon to keep it in orbit, but the gravity of Charon pulls Pluto and causes it to move. And so the Pluto-Charon system is rotating around a third point known as the barycenter of the Pluto-Charon system, the same way that the sun and the Earth revolve around that third point. Now, in the case of the Earth and the sun, you remember how small the Earth was. And so the center, the barycenter of the Earth-Sun system is very near the center of the sun, but it's not exactly in the center. And that tiny pull of the Earth on the sun is enough for us to measure. Scientists have developed exquisitely sensitive instruments, and they can measure the movement caused by the pull of the Earth's gravity on the sun. And by the same token, they can measure that same kind of movement on other stars in the galaxy. And so that's one of the methods used for finding exoplanets, planets revolving around other suns, other stars throughout the galaxy, because that gravitational attraction of the star with its planet and the planet with its star causes this motion of all of the objects together. And it's a fascinating study, and we know that there are a lot of planets out there. We've identified many planets, but how big, once again? We're talking about scale, we're talking about context. In this image, you can see in the top left the 4 terrestrial planets: Mercury, Mars, Earth, and Venus, or Venus and Earth, in size order. That's not in order away from the sun, but it's in increasing order of size. And so Earth looks pretty large in that picture, but the next picture beside it, there's Earth next to Neptune, Uranus, Saturn, and Jupiter. So in this image, Jupiter is enormous. But in that image number 3, you can see Jupiter, poor little Jupiter, down there in the lower corner next to Proxima Centauri, the nearest star, just barely big enough to be a star, but the closest star to our solar system. That is Proxima Centauri right there next to Jupiter, beside our sun, and then the star Sirius. Now, you know, it's really interesting to think about the context that we're talking about here. I said that Proxima Centauri is the nearest star to our sun, and that's true. It is about 4.2 light years away, and so if the sun were the size of a pea, then Proxima Centauri would be about 125 miles away. So it's hard to grasp the distances, because the sun is a little bit bigger than a pea, and the distances are just unimaginable, tens of thousands of years with any known technology that we have. Until we invent hyperdrive, we are probably not going to be visiting any neighboring stars anytime soon. So we'll see. If you come back and visit me in the year 3021, maybe we'll have made progress toward that, but probably not before then. Anyway, back to the slide here. So there's Sirius compared to Jupiter, but in slide number 4, you see that tiny little spot, that is Sirius, next to Pollux, Arcturus, and Aldebaran. Aldebaran is a red giant star and is unimaginably huge because there is Sirius, and you can see how big it is. But in image number 5, that tiny little pink little spot there in the lower left-hand corner, that is Aldebaran, next to Rigel and Antares and Betelgeuse. And Betelgeuse is, I have no words. But in image 6, there's Betelgeuse next to VY Canis Majoris, NML Cygni, and UY Scuti. Sorry, I have to read that because I can't remember those names. I don't know who came up with these names. But UY Scuti is the largest, so far, identified star in our galaxy. And here, for a sense of the scale of UY Scuti next to our sun, there we are. The surface of UY Scuti, and there is our sun for scale. So thinking again about the context and the distances and the sizes, and it's all completely beyond my comprehension, and I suspect really anyone's comprehension. But that's the way it is, and we know this to be true. Here's an image of our solar system with the bodies in the solar system to scale size-wise, not distance-wise. These planets would be much further away, obviously. If the sun, here's another little tidbit for you. If the sun were a 2-inch ball, the Earth would be essentially a grain of sand about 18 feet away. Now, it's hard for me to imagine that for the last 4.5 billion years, this grain of sand has been orbiting in a consistent orbit 18 feet away from a 2-inch ball. We know this to be true. We can calculate it with exquisite precision. But the fact, knowing how to calculate it is different from appreciating the fact of it. When I think of how this grain of sand 18 feet away from a 2-inch ball continues in this consistent orbit for billions of years, it puts me in a state of inability to appreciate how that really operates. Once again, we can calculate it. We have the gravitational constant and we have the formulas to calculate it, but the fact of it is different from a calculation of it. All that leads me to a little bit about the moon. Well, here is the first picture of the Earth taken from orbit around the moon. Now, in 1966, this picture was taken of the Earth from Lunar Orbiter 1, and everyone was so excited to see the Earth from orbit around the moon. And granted, this was, for 1966, a great photograph. But in 1969, here's another image of the Earth from the moon. Now, this image is really a special one to me, and I have always loved this image because I just think about what this image represents. This is the 1969 Apollo 11 landing in process, about to happen. And so Neil Armstrong and Buzz Aldrin are right there in the lunar module that you can see. Michael Collins is in the command module taking this photograph. And so if you think about it, and there's the Earth, of course. If you think about it, every human being in existence is in this picture, except one, and that's Michael Collins on the other side of the camera. And so it gives me a little bit of a feeling of loneliness. Michael Collins has been interviewed and talked about this, and he says he doesn't feel a sense of loneliness at all. He feels a sense of awe and wonder at the beauty and the majesty of the idea of going to another body, interstellar body, and having us walk there, and the fact that he was able to be involved in it was just amazing. So I have a lot of respect for Michael Collins, but I gotta believe that you'd feel a little bit lonely being the only human being not in a picture, and that's the way he was. Where did the moon come from? Well, we're not really 100% sure. As with so many of these things, we have a really good idea, but we don't have 100% certainty about a lot of things. The best theory about where the moon came from is that about 4.5 billion years ago, as the Earth was forming, as it was coming together, as the solar system itself was forming around the sun from the protoplanetary disk around the sun, a roughly Mars-sized body named Theia slammed into the infant Earth with such force that it essentially melted the entire Earth. The energy produced melted the Earth and threw off into space a significant amount of material. And that material went into orbit around the Earth and coalesced over time, over a fairly short time, into what we know as the moon today. And so the moon itself is probably the result of a titanic collision of this body, Theia, with the moon. We know a lot about how the moon operates. Well, at that time, at about 4.5 billion years ago, when the moon was formed, it was rotating much closer to the Earth, and the Earth was revolving much faster. And so the Earth, a day on the Earth was only about 19 hours long then, and the moon was closer. But in the succeeding 4.5 billion years, the moon is pulling away from the Earth, it's spiraling slowly out from the Earth, and the rotation of the Earth is slowing because of tidal friction, the gravitational attraction of the Earth and the moon. And so the Earth is slowing slowly in its rotation, so the day is getting longer and longer. That's why we have leap years every 4 years, because the Earth's rotation is getting slower and the days are getting longer, and so we have to continually add time to the calendar to account for that. And the moon is, as I said, spiraling away from the Earth. And so what you find is that the moon is moving away from the Earth at the rate of about 1.5 inches per year, spiraling out away from the Earth. And that rate of moving away from the Earth is about the same speed at which your fingernails grow. So you can look down at your fingernails, don't look at mine, but if you look at your fingernails and say, oh, they're this much longer than they used to be, you can also say that's about how much further away from us the moon is than it was before. And so interesting little way to entertain your children, maybe. Talk about how long their fingernails are. But there's the moon, and it revolves around the Earth. And we have one of the things that we know, I've just said that there's a lot of this that we don't know with 100% certainty. Much of it is best guess. Much of it is based on scientific hypotheses that are well tested but not absolutely proven yet. But one thing we know is that there is life on the Earth. If you're a philosopher and you want to question that, then we can talk about it after the show. But we believe there's life on Earth in any event. And one of the reasons that there's life on Earth is that the Earth is in the habitable zone, or the Goldilocks zone, around our sun. The Goldilocks zone is defined as that area where the planet revolving around its star is at such a distance where it's not too close, where it would be too hot for there to be liquid water on the surface because it would all have boiled away, and not too far away because there would be all liquid water would be ice. And so the Goldilocks zone is the area around a star at which its planet could have liquid water on the surface. Now, in our solar system, there are actually 3 planets in the Goldilocks zone. There's Venus, right on the inner edge of the Goldilocks zone. We don't believe there's any life on Venus because of the runaway greenhouse effect, and is causing it to have temperatures on the surface of Venus that would melt lead. And so there's probably no liquid water on the surface of Venus. There's probably also no life on Venus, except that some people have speculated about life possibly in the upper atmosphere, floating life in the atmosphere of Venus. Sounds a little bit science fiction-y to me, but there are people who are talking about it as if that were a serious possibility. I don't know, I'm not buying it, but we'll see. But then there's Earth, and then there's Mars. And we know there's liquid water on the surface of Mars because I just showed you pictures of it just a few minutes ago. And so we have 3 planets in the Goldilocks zone in our solar system. And that is one of the things that scientists looking for life out there in the galaxy, life in the cosmos, are looking for. They're looking for planets around their stars that have the potential for liquid water on the surface. Now, I know that I've just been talking about how here in our solar system, I'm not giving up anyway on the possibility of life on some other bodies in our solar system because of water in subsurface oceans. Those planetary bodies that we're talking about, Ganymede and Enceladus, etc., they're not in the Goldilocks zone, but they have most likely got subsurface oceans. That's not what we're looking for when we talk about potentially life-bearing planets out in the galaxy. We're looking for planets that are potentially life-bearing because they are a couple of things. Because they are Earth-like, meaning that they are roughly Earth-sized, and that they are rocky planets, so they're Earth-like planets, and we can know that based on measurements of the way they pull on their sun, and we talked about that a little bit. There are several different ways that scientists identify exoplanets, planets revolving around other stars in the galaxy. But we've identified planets that are roughly Earth-like, that are revolving around their star in the Goldilocks zone, in the habitable zone around their star, and that star is an Earth-like star. meaning it is a yellow dwarf star like our sun is. And so if we do that, if we look at the exoplanets that meet those criteria, roughly Earth-like, in the Goldilocks zone around an Earth-like star or a sun-like star, then we've looked at only a small bit of the sky, and we've found thousands of planets, exoplanets that meet those criteria. And so if we extrapolate to the entire galaxy, that definition of potentially life-bearing planet yields about 11 billion potentially life-bearing planets in our galaxy. If we expand that definition to include Earth-like planets revolving in the Goldilocks zone around their star, and say both yellow dwarf and red dwarf stars. Now, red dwarf stars are smaller and cooler and are less stable, more solar prominences, more solar flares, so they're a little bit less life-friendly, but as they age, and by age, as they get billions of years old, they tend to settle down. And so if we include, but they're also the most numerous stars in the galaxy, red dwarf stars. And so, but if we include both yellow dwarf and red dwarf stars, that number grows to about 40 billion potentially life-bearing planets in the galaxy. Now, I'm not a gambler, but the odds seem to me that if there are 40 billion possibilities for life out there in the galaxy, at some point, it's hard for me to imagine that we're all alone. But that's just me, and that's, whether you buy that or that line of logic is up to you. But anyway, we know that there are a lot of exoplanets that we call potentially habitable because of the criteria that I was talking about. And speaking of the galaxy, here it is. This is an image of the Milky Way Galaxy taken from Big Bend National Park down in South Texas. I hope you've been there. It's my favorite place in the world. I love Big Bend, been camping there many times, and I can remember taking my sons who are now 30, how old are they? 32, 34 years old, something like that. Who knows how old my sons are. When I took them there when they were 6 and 8, and we were able to look up in the sky and see the sweep of the Milky Way Galaxy, we were all just transfixed by the beauty of the Milky Way, because you can't see stars in a big city. And I have lots of friends, I have many, many students who have never really seen stars because they've lived in the city all their lives, and they've never been in a place with a really dark sky. Where you can really see the stars. So I would encourage you to go out to West Texas, to Big Bend. I mentioned the McDonald Observatory earlier. That's way out in West Texas, run by the University of Texas, and the reason it's there is because it's about the darkest sky in North America, right there where the McDonald Observatory is. It's an absolutely amazing experience. You should definitely try it. But there is our galaxy. Here's another picture of our galaxy. And I took this picture, actually, not really. I didn't take this picture. But you can see the sweep of our galaxy here. We live in the Milky Way Galaxy. It is a spiral galaxy. There is the Scutum Centaurus arm. There's the Perseus arm. And if you look here, that little wisp, that little line of star material there coming out is called the Orion spur of the Milky Way Galaxy. And if you see where it says the sun and draws the line, that's about where we are. That's the Orion spur. The big line of stars below us, that's the Perseus arm. The big sweeping arm on the top is the Scutum Centaurus arm. And you can see right there on the Orion spur of the Milky Way Galaxy, that's where our sun is. So we are a tiny little star, about a third of the way out, away from the center of the Milky Way Galaxy, which is itself about 120,000 light years across. And we believe that at the center of the galaxy, the Milky Way is a multi-million solar mass black hole that we refer to as Sagittarius A star. You can see it written there, and we say Sagittarius A star, and that doesn't mean it's a star, it's a black hole, but the star indicates that is that body, the central black hole. So we've got a galactic portrait. That's the way the Milky Way looks. So now we know where the Earth is with respect to our solar system. We know where our solar system is with respect to the Milky Way Galaxy. Where is the Milky Way Galaxy with respect to the larger context in which it exists? Well, the Milky Way Galaxy is right here. You can see the little red dot. That's where our Milky Way Galaxy is, on the outskirts of our local galactic supercluster, which scientists have named Laniakea, which is a Hawaiian word meaning immeasurable heavens. This is our local supercluster of galaxies, consisting of somewhere in the vicinity of 100,000 galaxies. And the distinguishing characteristic of our supercluster is that everything in our supercluster is moving in a direction that's referred to as the bulk flow toward the great attractor here in the center of our galactic supercluster. You can see it maybe a little bit better here. The great attractor in the constellation Centaurus, there the red dot is the Milky Way Galaxy, and all those lines indicate the bulk flow flowing toward the great attractor at the center of Laniakea, our local galactic supercluster. What is the great attractor? Nobody knows. Some enormous, unimaginable gravitational anomaly. Nobody really knows what the great attractor is, but we know that we're moving in that direction. And so that's where our Milky Way Galaxy is. But where is our local galactic supercluster? It gets bigger and bigger. Well, our galactic supercluster is right next door to our neighbor, the Perseus-Pisces galactic supercluster. And the distinguishing characteristic there is that everything in that supercluster is flowing toward its own great attractor. You can see the dividing line where we're flowing toward ours, they're flowing toward theirs. That's the separation point between our galactic supercluster and theirs. Now, this is a lot of talk, but how do we know all of that? Well, we know it from a whole list of avenues, a whole list of lines of evidence. This is one of those lines of evidence. This is the Hubble Extreme Deep Field photograph. At one point, and it's a fascinating story about how this photograph came to be, but the director of the science team that was responsible for the Hubble decided that he was going to point the Hubble Space Telescope, which every astronomer in the world was competing for time on. If you're an astronomer, you're always competing for time on the telescope. And when he decided that he was going to point the Hubble Space Telescope at nothing, which is what he was going to do, for an extended period of time, everyone thought he was crazy. Because he decided to point this Hubble Space Telescope at an empty spot in the galaxy and left the Hubble Space Telescope's shutter open for about 10 days. And what resulted was this photograph. So we have 10 days of light streaming in. And instead, now, I want to tell you this, the spot in the galaxy that he was pointing the Hubble Space Telescope at was roughly the size, the apparent size, of a tennis ball from 100 yards away. So imagine you put a tennis ball down on one goal line of an American football field, walk to the other goal line of the American football field, turn around and look at that tennis ball. And that tennis ball is the apparent size of the spot in space that he pointed the Hubble Space Telescope at. And this is the picture that resulted. And as far as we knew, it was empty space. But obviously it turned out not to be empty space at all. What it showed was that there was a further life is probably a bad word to use. There's further existence of galaxies and pulsars and novas and all those things way out there that we had no idea of until we took this Hubble Extreme Deep Field photograph. Now we can tell a lot about the universe based on this photograph because we're able to do things like measure brightness and we're able to measure distances, and there's the distance ladder that we can talk about another time, but there's a lot we can learn about the galaxy and planets and stars and other galaxies from this photograph. There's also the two-mass redshift survey, which was done with a series of telescopes, small telescopes, who were able to, over time, capture images of over 300 million individual point sources of light in the universe. Over 300 million point sources. And not only could they identify the point sources, but they were able to measure the redshift of those those sources of light. And so they could tell whether they're moving toward us or away from us, and how fast and how far away they are, with a reasonably high degree of precision. And so when you look at the existence of all of these points out there in the universe, you can, if you're able to see this image up close, you can start to see lines, you can start to see what almost looks like a pattern. And when you gather all this data and make a picture of what it really looks like, this is it. This is a picture of our universe at the very largest scale. There is a name for this, and it's referred to as the cosmic web, because it looks like that the matter and energy exist in our universe on these filaments, these unimaginably enormous filaments that are interspersed with comparatively empty spaces. Why it's exactly that way, nobody really knows. Tiny inconsistencies at the moment of the Big Bang resulted over the 13.7 billion years since the Big Bang in this kind of pattern of reality. And it's just amazing. It always reminds me of like a neural network, brain matter. And I'm not suggesting that the universe is alive, but if you look at this image, it looks like nerves connecting with each other. And it's just an amazing, awe-inspiring to me photograph. And it results from, as I said, about 13.7 billion years of growth since the Big Bang happened. And there's a lot about that we still don't understand. We understand more and more and more about it. But one of the things that has been a surprise in the last few decades was the discovery that the expansion of the universe is accelerating. Completely unexpected result from the examination of images and of understanding of the redshifts of galaxies and the study of the entire universe. The universe is expanding, which is not a surprise since it started with an explosion, or what we refer to as an explosion. But that expansion is not consistent. That expansion is accelerating. And we all know from Newton's laws of motion that an object in motion stays in uniform motion unless acted on by an outside force. And so for the growth of the expansion of the galaxy or the universe to be accelerating, there must be an outside force acting on it. And what is that? Well, that's largely how we came up with, that's one of the main reasons we came up with this idea of dark energy. Dark energy is not a description except insofar as it means that the whole idea is dark to us. We have no idea what it is, and so they just call it dark energy, but there must be some energy out there causing the expansion of the universe to accelerate. And so we have this idea of dark energy. And in fact, baryonic matter that makes up you and me and this clicker I'm holding in my hand, and the Earth and the sun and all the planets and all the stars and all the galaxies and all the matter in the universe is baryonic matter. But that makes up a small percentage of the total mass and energy in the universe, probably less than 5%, because about 20% is what we call dark matter, which is, as dark energy is not understood at all, although we have experiments trying to identify it. We've tried to identify dark matter, and there are some scientists who think they have a pretty good idea what it might be, and so they've built these experiments to try to identify it, try to detect it, but they've been unsuccessful so far. But then 70 or 75% of the total mass and energy of the universe, and remember that according to Einstein's equation, E equals mc squared, matter and energy are the same. About 75% of it is this dark energy. And so you and I and all the other baryonic matter in the universe make up only a small percentage of the total mass and energy of the universe. The universe, I speak of that in the singular form because we only have our own universe to worry about, but scientists have one of their favorite little theories or hypotheses, I suppose, is the hypothesis of the multiverse and how our universe is only one among a potentially infinite number of other universes. And so this is just a science fiction image of what the multiverse might look like. Nobody knows because by definition we cannot gain information from outside our universe. That's essentially how our universe is defined. The maximum extent based on the travel time of the speed of light from which we could receive, even potentially receive information. Beyond that is outside our universe. But there are probably, or I say probably, the hypothesis is that there is a multiverse. But how would you ever, because we can never gain information about it, how would you ever prove a hypothesis like that? Well, some scientists think that they may have found evidence for the idea of the multiverse in this image. This is an image of the cosmic microwave background, the background energy left over from the Big Bang. And if you look at the universe on the largest scale and measure the temperature of the universe on the largest scale, there is very great uniformity with tiny differences, and that's what these differences in color are. But those little spots there that look a little bit like bruises, some very speculative scientists have speculated, again, that those represent interference or bumps into other multiverses, contact with other multiverses. And so who knows? It's all completely speculative at this point, but it's fun to think about. And so there we go. But I've talked a lot already now, and I'm finally getting to the real point of all of this. Why are we here? Why am I talking about all this? Well, this image really is the reason I've been talking for all this time. This is the whole point. This is a picture taken in 1990 on Valentine's Day by the Voyager 1 spacecraft when it was 4 billion miles away from Earth. The Voyagers 1 and 2 were launched in 1977, and they've been traveling away from the Earth ever since, both of them, Voyagers 1 and 2. Now, this picture was taken by Voyager 1 in 1990. One of the things about those Voyager spacecraft is that they are powered by RTGs, radioisotope thermoelectric generators, which have a small quantity of plutonium inside each of those generators. There are 3 on each of the spacecraft. And plutonium, obviously we all know, is highly radioactive, and radioactive decay produces heat. That heat is passed through thermocouples, converted into electricity to power the instruments on the Voyager 1 and Voyager 2 spacecraft. But as plutonium decays, there's less and less of it left, and so there's less energy left to convert into electricity. And so over time, mission managers have had to turn off non-essential instruments in the Voyager 1 and Voyager 2 spacecraft. Voyager 1 and 2 are now both outside the solar system. They are roughly 21 hours of light travel time away from Earth, and that's at over 186,000 miles per second. 21 hours away, about over 150 astronomical units, which is the distance from the Earth to the Sun, over 14 billion miles away, and they have both passed through what's known as the Heliopause. The Heliopause is that region of space where the solar wind, the ions and charged particles flowing outward from the sun, the energy flowing out from the sun, is balanced by energy flowing in from interstellar space. And so inside the heliopause, inside the heliosheath, there is a predominance of solar wind flowing out. Outside the heliopause in interstellar space, there's a predominance of cosmic rays flowing in, and at that point, at the heliopause, they balance. And in 2012, Voyager 1 passed through the heliopause into interstellar space. In 2018, Voyager 2 passed through the heliopause into interstellar space. So we have two actual human creations that have exited the solar system. They've left the house. And we are yet still receiving science information from these spacecraft. They both have transmitters, and I said they turned off unnecessary instruments that were not necessary for their science mission. Well, one of the instruments that's still on is the particle detector, and that's how we know where they are. And they broadcast back to Earth using a transmitter. Each of them has a transmitter that is powered at about 23 watts. And so from over 14 billion miles away, outside the solar system, we are receiving a signal from Voyager 1 and Voyager 2 that is transmitted using a power about equivalent to your refrigerator light bulb. And so the receiving technology that we have to be able to receive, understand the broadcast from the Voyager 1 and Voyager 2 spacecraft just blows me away. 23 watts from 14 billion miles away, and we can still receive it and understand it. They're both still moving away, and I have a picture here of Voyager 1 and Voyager 2 as they are passing through the heliopause. But I'm getting away from my picture. The reason we're here. What is it about this picture that is so special? Well, you may, if you've looked at it, have realized that that dot right there is what is special. When in 1990, mission managers were turning off non-essential instruments, the cameras were still turned on at that point, and Carl Sagan, one of the mission scientists, worked with the mission managers to do one last thing with the cameras before they turned them off. And they took what's known as the family portrait. And this is one of the images from the family portrait taken by Voyager 1 in 1990, right before the cameras were turned off. And you may have realized that that little blue dot right there is the Earth from 4 billion miles away. When Carl Sagan saw this photograph, he was very excited by this photograph and excited by what it could possibly represent. And he named it the Pale Blue Dot. And he wrote a book called The Pale Blue Dot. It's on my nightstand at home, highly recommended reading. And I'm going to read to you from the next couple of slides what Carl Sagan wrote, some of the things that Carl Sagan wrote about the pale blue dot. From this distant vantage point, the Earth might not seem of any particular interest. But for us, it's different. Consider again that dot. That's here, that's home, that's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there on a mote of dust suspended in a sunbeam. The Earth is a very small stage in a vast cosmic arena. Think of the rivers of blood spilled by all those generals and emperors so that in glory and triumph they could become the momentary masters of a fraction of a dot. Think of the endless cruelties visited by the inhabitants of one corner of this pixel on the scarcely distinguishable inhabitants of some other corner. How frequent their misunderstandings, how eager they are to kill one another, how fervent their hatreds. The Earth is the only world known so far to harbor life. There's nowhere else, at least in the near future, to which our species could migrate. Visit, yes. Settle, not yet. Like it or not, for the moment, the Earth is where we make our stand. There's perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known. And so when I read that, when I hear those words, it brings up a lot to me. One of the things that it brings up to me is this. You probably are familiar with Percy Bysshe Shelley, the poet, who wrote long ago, not long ago in cosmic terms, but long ago in our lives, a poem called Ozymandias. And I'm going to read this to you as well. Sorry for reading so much. I met a traveler from an antique land who said, "Two vast and trunkless legs of stone stand in the desert. Near them, on the sand, half sunk, a shattered visage lies, whose frown and wrinkled lip and sneer of cold command tell that its sculptor well those passions read which yet survive, stamped on these lifeless things, the hand that mocked them and the heart that fed. And on the pedestal these words appear, my name is Ozymandias, King of Kings. Look on my works, ye mighty, and despair. Nothing beside remains. Round the decay of that colossal wreck, boundless and bare, the lone and level sands stretch far away." So that's one of the things that I think about. Another thing I think about is this. I don't know how many of y'all might be familiar with Horton Hears a Who? One of my favorite Dr. Seuss stories. And the story goes that Horton the elephant finds a speck of dust. And because of his huge elephant ears, he's able to hear what others can't hear. And he hears sounds coming from people living on the speck of dust. And there's an entire civilization on that speck of dust, which ultimately reveals itself to Horton and to the others. I don't know if in my mind we are Horton or we are the Whos, who are the people living on that speck of dust. But in either case, it comes to mind when I think of Ozymandias and when I think of our pale blue dot. And so today I've gone from the farthest reaches of the universe to our Milky Way Galaxy, to our solar system, to our warm, wet, life-giving Earth, and back to my front porch. And when I think about all of this, another thing that comes to mind is the fact that in each of our lives, we are given about 3 billion heartbeats. And I would beg of you not to waste them. Because in the immortal words of Gandalf the Grey, all we have to decide is what to do with the time that is given to us. And so, what does all that mean? What does it make you think? I've asked that question a lot of people, students and others who've seen this presentation. The universe is a big place. Life must be out there somewhere. The Earth seems small. And the last one is the one that to me is the most important. It makes me feel insignificant. The tiny speck of the Earth against the entire cosmos. The insignificance of the Earth is manifest. But is that a good thing or a bad thing? Well, scientists these days are studying the science of awe. And we find that a feeling of awe produces a feeling of insignificance, just as my students have said. But that feeling of insignificance leads to a diminished sense of self or humility, which can be a very good thing. Humility is a good thing. It can lead to an increased sense of connectedness with others, with other people, and with the world around us. And in today's increasingly disconnected world, I hope that the message here that the insignificance of the earth leads each of us to feel that humility and an increased sense of connectedness with those around us. And that's all. Thank you very much for being here. Live long and prosper.